Hello everyone, welcome to the last lecture of the second chapter. So basically we're going to solve problems related to acids and base and related phenomena. So we started this chapter by talking about acids and base and the definition, and then talking about weak acid, strong acid, and try to calculate the pH of the solution when these acids are added to the solution. And we look at different approaches to do so. For example, using algebra, trying to make some assumption to simplify this algebra. The other approach was basically using graphs, and another approach was using computers. But eventually, we were following the same path of uh, first formulating the system in terms of the speciation and all the governing equations, which was mass balance, charge balance, and equilibrium equations. And then based on that, we talked about some acid-base related phenomena, such as titration. We talked about buffers. We talked about alkalinity. And at the end, we talked about gas-liquid equilibrium going towards open systems. So the first question is basically asking us how much of a weak acid or a salt of a weak acid we need to add to pure water in order to adjust the solution pH at either something below 7 or something higher than 7. So the first part, basically, we're adding just the weak acid itself. So how much we need to add HOCl in order to decrease the pH of pure water, which is at 7 initially, to a pH value of 4.3. Since we are adding a weak acid, so we are donating some proton to the solution, so it makes sense that the pH drops when we add this weak acid. Like any other acid-base question, we always start with speciation. So in this case, when we add HOCl to the water sample, we basically not only have this hydroxide and proton species, but also the new species that are added to the solution. So just keep in mind, we have both HOCl and also OCl minus, because this is a weak acid, we don't have the full dissociation. If it was, let's say, HCl, then we don't have HCl as a species. We only have Cl minus because it's a strong acid, it fully dissociates. So after species, we always talk about charge balance based on the species, the combination of all the positively charged species is equal to the negatively charged species. This was the OCl minus. Then we always have this mass balance for closed systems. Just keep in mind this is a closed system, so we have this mass balance. So the total OCl that we add initially would be in the form of either HOCl and OCl minus. And the ratio, as we know, is a function of pH. So we also have the equilibrium equations. Equilibrium equations, obviously, for water, but we're skipping water for now. We have this acid-base reaction of Ka. Let's actually write down the equation itself first. So we basically have the deprotonation of HOCl to OCl minus and H plus. And we have Ka for this reaction as OCl minus times H plus divided by HOCl. So these are just the general equations we have. But for this particular case, we basically have the pH. So we need to calculate the total concentration of the weak acid. So basically, we need to calculate this. So to calculate this, we need to basically calculate the individual species, HOCl and OCl minus. So when we look at this charge balance, we see that since we know the pH, we know what's the concentration of proton, and then based on Kw, we can calculate OH minus concentration. So this would be pretty straightforward to get OCl minus fraction of the total OCl. So if, say this is equation 1, based on equation 1, we have OCl minus equal to H plus minus OH minus. So pH is at 4.3. Therefore, the concentration of H plus is 10 to the minus 4.3 molar. And so OH minus is 10 to the minus 9.7 molar. So based on this, the OCl minus concentration would be 10 to the minus 4.3 minus 10 to the minus 9.7. So as you see, this value is significantly smaller than this, so we can ignore it. So the OCl minus would be almost equal 10 to the minus 4.3 molar. So now we know this contribution of concentration of total OCl, and also we know the pH, so we basically can take advantage of this equilibrium constant, the equilibrium constant that relates OCl to HOCl concentration. So basically if we have 2, we can rearrange it, then HOCl concentration would be basically OCl minus H plus divided by Ka. All of them are given, and OCl minus we just calculated, so this would be 10 to the minus 4.3. H plus concentration is also 10 to the 4.3 minus 4. And then the Ka value is 10 to the minus 7.53. Then we have 10 to the minus 107 molar for the concentration of all HOCl. So as you see, at this condition, the dominant species is HOCl, but we can just combine these two to get to total OCl concentration. So total OCl would be, as we mentioned, OCl minus plus HOCl. Then this would be 10 to the minus 4.3 plus 10 to the minus 107, which should be 0.08 molar. So basically what it says is if we add 0.08 molar of HOCl, then the pH would be 4.3. Just pretty simple. Since the pH was given, the math was relatively simple. If pH wasn't given, we had to do a little bit more work on the mathematical part. So now the second part of the question is basically asking us, now we want to adjust the pH to a higher value. So to do so, we cannot add the acid itself, because adding acid would result in decreasing the pH. Rather, we want to add the salt of a weak acid. So the salt of a weak acid here, for example, we add NaOCl for this particular case. But then the question is asking how much NaOCl we need to get to the pH of 9. So basically the same thing. We have to do the same thing as before, but this time, for example, the charge balance term is different, and slightly the mass balance term. So let's say if we add NaOCl to the solution, then we have full dissociation of the salt, what we assumed in this chapter. So we could get Na plus OCl minus. And we know for 1 mole of NaOCl, we produce 1 mole of Na plus and 1 mole of OCl minus. So total Na, which is equal to the Na plus, would be equal to total OCl, which is equal to HOCl plus OCl minus. Just keep in mind, when you introduce OCl minus to the solution, at equilibrium, you have both OCl minus and HOCl depending on the pH. So now we're dealing with a new charge balance. Basically, we have Na plus also in the charge balance. So as a positively charged species, this would be H plus Na plus is equal to the right-hand side of the charge balance as before. So now when we look at this equation, we see that there are two unknowns. So this means it's a little bit tricky here, but if we combine basically these two, then it would be pretty simple. So basically what we understood here was the concentration of sodium, which is coming from the total concentration of sodium, is equal to the total concentration of OCl, which is basically HOCl plus OCl minus. So if we combine these two, we basically have H plus HOCl plus OCl minus is equal to OH minus plus OCl minus. And as you see, we can basically simplify this. And now we have only one unknown and one equation because we know the pH. Then the only unknown would be HOCl, which would be equal to OH minus the H plus. So pH is at 9. So the H plus would be 10 to the minus 9, and obviously OH minus would be 10 to the minus 5. Then the concentration of HOCl would be almost 10 to the minus 5. So last time we actually mathematically first calculated OCl minus, and then using the equilibrium constant, we related to the HOCl, but now we're doing basically the opposite work. So based on the equilibrium constant, we know that the OCl minus times H plus divided by HOCl, this would be the equilibrium expression. So OCl, the only unknown, would be Ka times HOCl that we just calculated, divided by the H, which is known based on the pH. So this would be 10 to the minus 7.53 times 10 to the minus 5 divided by 10 to the minus 9. Then this would be roughly 3 times 10 to the minus 4 molar. So in this case, the total OCl, which would be the total Na, or the total concentration of the salt that we need to add, this would be HOCl plus OCl minus. So then it would be 3 10 to the minus 4 plus 10 to the minus 5, this which would be 3.1 10 to the minus 4. So basically if we add 3.1 10 to the minus 4 of NaOCl, then the pH would increase from pure water at 7 to a pH of 9. So this is a very useful calculation to adjust the pH based on the weak acid itself or a salt of a weak acid. So either to increase the pH or to decrease the pH. So the second question is basically more on the graphical side of the pH evaluation. So the question is asking us to determine first, what was added to water that we get such graph, and then what was the concentration, and later try to calculate the pH of the solution based on the graph that is given. So the first part is basically what was in the solution. So if it was just pure water, we would have only OH minus line and H plus line. But it seems we have this pair of ammonia, ammonium. So obviously we have somehow ammonium was introduced to the system. And then when we look at this species, we see that ammonium was added as ammonium chloride. So we basically added ammonium chloride. So it turned to ammonium plus Cl minus, and then this was producing ammonia plus H plus. And when you look at it, we have individual lines for each species and ammonia. And obviously we have hydroxide. And now the second part of the question is asking, what is the concentration? What was the total concentration of ammonium chloride? When we look at the graph, we see that the Cl is not a part of any reaction. So the concentration must stay the same, and that should be the total concentration. So the total concentration of the salt is equal to the total concentration of Cl, which would be, in this case, P of that concentration is 4, so the concentration would be 10 to the minus 4 mole was added. So 10 to the minus 4 molar of ammonium chloride was added, and then we get to this sort of graph. We could also do the same thing. Total salt would be equal to total ammonium, but then it would be a little bit tricky. Then we have to have like this total ammonium by just basically combining all these two lines. So it would be easier to just go with Cl minus. So that's, till now, we know what was added to the solution, and then we know its concentration. Now, the question is asking us, we estimate the solution pH only by the graph. So we know the species, so we can basically drive the charge balance. So the species, which are represented by individual lines in the solution, are H plus, OH minus, ammonium, ammonia, and Cl minus. So now we can do the charge balance, because that was the core of actually finding the pH using graphs. So charge balance, in this case, would be H plus ammonium equal to OH minus plus Cl minus. And the way we did was basically the left-hand side of the graph was equal to the right-hand side of the graph in order to satisfy the charge balance. So the left-hand side is basically H plus ammonium, and then the right-hand side is basically OH minus plus Cl minus. So now we need to construct this LHS and RHS on the graph. So to do so, we need the graph again. So now that we brought the graph and also the equation, here we just need to construct this LHS and RHS line, and when they cross each other, that's the pH point. That's how it works for graphical solutions. And then we also in the lecture talked about how to go from how to combine two individual species on the P graph. How does that work? We basically take the higher value in terms of the curve. So let's start from the LHS. So we are dealing with two lines, H plus, and also the OH, NH4 plus. So when we start from the left, the H plus values are bigger. And then at this point, ammonia is bigger. And continues to here, ammonia would be a bigger value. So this would be our left-hand side graph. Then the right-hand side, we're basically dealing with OH minus and Cl. So this would be the Cl line and this would be the OH minus. So the curve would be relatively easy. So we'll start from here. Then from here, the OH minus is bigger. So this would be our RHS, right-hand side. And now we see that because we don't have the resolution, somewhere between here, we have our pH. So somewhere here, we have the pH. But we don't have a good resolution. So one way is to basically revisit RHS and LHS in a way that we have a higher resolution for to find that exact crossover of LHS and RHS. So to revisit that, we know that basically the total concentration of ammonia is equal to the total concentration of Cl. And the total concentration of ammonia would be, so this would be ammonium plus ammonia, and the total concentration of Cl would be basically just the Cl itself. There's no other species with Cl. And now we combine this into the charge balance. So for charge balance, if you remember, we had H plus ammonium, plus ammonium. And on the other hand, we had hydroxide plus Cl minus. And now instead of Cl, we just say NH4 plus the ammonia term. Or to simplify it, basically what happens is we can, the ammonium term will cancel. So we get 2 proton equal to hydroxide plus ammonia. So it seems we have now a different terms for RHS and LHS. Our LHS would be simply the pH line, and our RHS would be the hydroxide line plus the ammonia line, not the ammonium. So now we need to bring the graph again and then do this revise LHS and RHS. So if we bring the graph again, now this time we're dealing with a different RHS and LHS. So our LHS is basically the H plus line. So it would be simply this line. This would be our LHS. And now our RHS would be hydroxide plus ammonia. And just keep in mind the one that is bigger. So starting from here, we see that ammonia line is bigger. And up to here, but then the hydroxide line is bigger. So this would be our RHS. So we were expecting actually a pH somewhere between in this region. So let's say between 4 and 9. And now we have the exact value, which would be pH of roughly 6.5 or 6.5 roughly, because there's just one point and it's visible and it has a high resolution. So basically what we did in this example was the PCPH diagram was given. We didn't know anything about what was added to the solution and what was the concentration. I mean, it wasn't given by the question. Then we figure out, okay, now we know what was added based on some logical discussion that we had. For example, this was added. And then looking at the total concentration, we were able to find the total concentration of the salt that was initially added to the solution. Then later we had this charge balance term, LHS, RHS. The first LHS, RHS, we sort of failed because the resolution wasn't high, but later we twisted a little bit. By taking the mass balance, combine it with the charge balance, we were getting the revised LHS and RHS, which was basically easier to find that point representing the pH of the solution. So pretty straightforward. So the third question is basically we are adding a salt to a solution, and that salt contains both anion and cation could introduce a new acid base to the system. So previously, for example, in the previous example, we added ammonium chloride, so NH4Cl. So the cation was introducing an acid base to the system. So ammonium, as a result of that, we have this ammonium-ammonia reaction. But here, the anion also, this carbonate, is also introducing a carbonate-related acid-base reactions. So basically, by adding one salt, we're introducing two acid base to the solution. So the question is asking us first, basically, to look at the speciation, all the reactions that might happen, and also all the mass balances. So we start with speciation. So let's first, before the speciation, we're adding 10, or not 10, we're adding ammonium carbonate. So this would produce 2 mole of ammonium plus 1 mole of carbonate. And so now we can, from the beginning, tell that the total concentration of ammonium is basically twice as the initial concentration of the salt, because 1 mole of this guy is producing 2 mole of ammonia. And we have 10 to the minus 3 of the salt, so this would be 2 10 to the minus 3. And the total carbonate in the system, just not using total, we can just remove this charge to make it simpler. It would be 10 to the minus 3 molar. So that's about what we're introducing to the system. And now, as a consequence of this introduction, we have this acid-base reaction. So in terms of the species, we could, let's first, actually, before the species, we can actually write all the equations. So this ammonium can participate in an acid-base reaction, equilibrium to ammonia plus H plus. So this would be Ka of ammonia. Therefore, this would be NH3 H plus divided by NH4 plus. So that's one of the equations we got. And we also have this carbonate to the system. So we're going to deal with the carbonate system. So the most protonated version produces bicarbonate and hydroxide and proton. This would be Ka1 HCO3 minus, like pretty standard description of an acid-base reaction. H2CO3, and we have HCO3 minus going to carbonate. Ka2, just keep in mind this Ka2 is Ka2 of carbonate system. And the bicarbonate. So now we can write the species. We basically have always this H plus OH minus. Now we're introducing ammonium to the system. And as a result of that, we also have ammonia. Then we're introducing bicarbonate to the system. So we're going to have H2CO3, HCO3 minus, and CO3 2 minus. And yep, that's it. So we have 1, 2, 3, 4, 5, 6, 7 species. So we basically need 7 equations. Let's see how much we got so far. So we have 1, 2, 3, 4, 5. We have 1 for water, would be 6, like Kw of water, I mean. So the only equations we need, one more left, and that would be, just let's also write this mass balance one more time. So the mass balance, the total CO3, which was 10 to the minus 3 molar, would be basically all the species that contains carbonate, HOH, CO3 minus plus CO3 2 minus, and then the total of ammonium would be basically ammonium plus ammonia, which would be 2 10 to the minus 3. And the last equation would be basically the charge balance, all the positively charged species. In this case, H plus ammonium would be equal to OH minus, HCO3 minus, plus 2 CO3 2 minus. So basically we have now 7 species, 7 equations, and we should be good finding the solving for the pH, depending on what kind of approach we want to take. And this particular example is asking using the Excel spreadsheet, but we could basically use any other method that we wanted, like graph, or just using an algebra. So now in part B, we're going to use Excel to solve for the pH of the solution when 10 to the minus 3 ammonium carbonate is added to the solution. So now if you look at the Excel that you see, we have basically 2 acid-base reactions. So keep in mind we have 2 sets of alpha values. So this is alpha 0, alpha 1, alpha 2 for carbonate system. And then later we have this alpha term for basically ammonia system. And since these are pH dependent, it's a function of pH, and obviously they have these 2 systems have different K values. So the alpha 0 values for carbonate system and ammonia system are obviously not the same. And as you can see also here. So you need to define alpha system first for carbonate or for one of the system, then calculate the species as you see here based on the alpha term, and then go for the alpha of the other one, the other species, calculate the species itself based on the total that we just talked about, and it has to be twice, the ammonia total has to be twice as the carbonate because it was added as ammonium carbonate, not ammonium bicarbonate, which in that case would be equal. And then this charge balance term that we always have, all the positively charged minus the negatively charged species, considering the stoichiometric coefficient, and then look for where we have change in pH. In this case, we have between pH of 9 and 10. So we go and zoom between pH and 9 and 10. So what is happening here? The second table, basically doing the same thing, alpha values and the concentration values, but we zoomed in, and now here, when we look at the table, we see that here is changing. So between pH of 9.15 and 9.2. So the pH is somewhere between 9.15 and 9.2, and that's a pretty high resolution. So I brought the graph here. As I mentioned on the first part, we see that the pH is between 9 and 10. And here we increase the resolution in the bottom, and then we see that it's between 9.15 and 9.20. So we assume pH is roughly 9.15. So now that we have this speciation, we can simply making it a p-value. So if we have a concentration of ammonium, we can have like a concentration, we can have like p ammonia minus log of the concentration of ammonium. So it would be very simple if you have this Excel sheet to construct the PC-pH diagram for all the species that are involved. So if we go back to the Excel file, we see that if we basically have this PAC-pH diagram here, I'm taking all the individual species from the previous table, from this table on the left, and just doing a minus log. Just so you look at the fx here, it's minus log of what was there, what was calculated as a function of pH. Then I can have like this basically graph of PC pH for all the species. So it looks more complicated because it's more involved, because we're dealing with two different systems, not just one. So obviously we have more lines, but the logic would be the same. You don't consider individual systems as themselves, but basically a combination of two in one graph. So they all are in the same solution. And so you cannot just calculate the pH change or the pH contribution related to the ammonia system versus the pH contribution related to the carbonate system. So now, every time we have a PC-pH graph, that means there's a good chance we can also use the graph to quickly calculate the pH by using that technique we talked about in the previous example, by going for LHS versus RHS. So here, let's see how difficult it is, or how complicated it would be if we go for this relatively complicated system to do this LHS RHS. So the part C is asking basically evaluating pH of the solution using this graph. So what we figured out and what we talked about before and what we saw in the previous example. So when we look at the charge balance, we see that we have proton and ammonium is equal to hydroxide plus bicarbonate plus the carbonate term. So the RHS, the LHS, would be H plus ammonia. So that's one line. And our LHS would be basically all the species here, all the negatively charged species. So now let's see if we construct these two lines, how does it look? Is the resolution good enough or not? So that's the question now. In the previous case, it wasn't good enough, so we had to revisit the RHS, LHS, but we'll see here. So the first LHS is basically proton, so this line, and ammonium, the red line. So if we construct the LHS, this would be basically this line up to here, and then ammonium is bigger all the way. So this would be our LHS. So now let's construct the RHS. This 2, the factor of 2 minus 0.3, let's just, because it's hard to have a good control, so we go slightly higher than this, whatever line is bigger. So when we start from this side, we see that first this is bigger compared to hydroxide and bicarbonate. Then here the bicarbonate line is bigger a little bit, and then the hydroxide line is bigger. So this would be something like this. Here up to here, bicarbonate, and then carbonate, and then the other term. So basically it has to be a little bit higher, that point minus 0.3. So, and this would be our RHS. And when you look at it, my drawing wasn't the best, but when you look at it, there's only one point, and that point is very close to 9. So this would be the pH, almost 9. So it is very close to what was predicted using the Excel file. So again, this drawing was not the best, but there's no conflict before here, but there's just a one crossover between the two lines here, and then it continues with the higher value. So the pH was also predicted to be 9, which is very similar to what we had using the Excel spreadsheet, which is more accurate. It doesn't rely on the observation, but it relies on basically the actual mathematical operations. So basically this question, what we talked about, what we covered was a closed system that we added a salt that not only cation, but also anion was introducing an acid-base reaction. So the cation was introducing ammonia, and then the cation was introducing the whole carbonic acid solution to the system. So that's why we had this relatively complicated framework of species in the solution. So the last question is basically talking about a solution in equilibrium with two acidic gases. So solution in equilibrium with a gas. That means we're going to talk about an open system. So here, as I mentioned in the lecture, when we talk about open system, we lose one mass balance equation, but we gain one gas-liquid equilibrium equation. So that would be the core. That's what dictates the first or the most protonated version of the species for the acid. So for example, if it's CO2, the partial pressure of CO2 would dictate the concentration of carbonic acid itself in the solution. Now, the solution is actually exposed to two gases. One is carbon dioxide and the other one is hydrogen sulfide. These two have, from the gas-liquid point of view, they have different Henry constant. So they partition differently. And also when it comes to the solution, they also have different pKa's. So, and they both are diprotic acid. So they have different pKa1 and pKa2. So the first part of the question is asking us to use Excel in order to basically calculate the pH. What would be the pH? So the core of using Excel for the previous case was basically using alpha term. And alpha term, it relies on the total concentration. But here we don't have that total concentration, or it's not constant. So we have to relate everything to the concentration of something that we know, and that's the most protonated version of the acid. So for example, in terms of the carbonic acid, we have to relate the concentration of the other two species, such as bicarbonate and carbonate, to the concentration of carbonic acid, because the concentration of carbonic acid is a function of the gas partial pressure. So let's start first just driving general equations for the system that is exposed to air. So to start, we have both CO2 gas and H2S gas. So what happens is basically first we have the CO2 gas in equilibrium with the solution, so CO2 in the solution. And as we talked in the class, basically we can consider this to be the carbonic acid in the solution. And then this is governed by the Henry's constant, because we have the concentration, we need the concentration, and we have the partial pressure, so it's better to go with PM of CO2. And then we have, when we have H2CO3 in the solution, then it comes to the acid base in the solution equations. So H2CO3 in the solution, first protonation, H plus, and then this would be Ka1 of CO2. Let's call this CO3. I'm just showing that the carbonate system. And then the second one, HCO3 minus, is deprotonating to CO3 2 minus plus H plus. Then this would be Ka2 of CO3. Then we have the second gas now, H2S. From the gas phase is going to the aqueous phase, governed by the Henry's constant for H2S. And then we have this deprotonation of H2S in the solution, HS minus plus H plus, Ka1 of S, and then HS minus is going to S2 minus, fully deprotonated, and then Ka2 of the system S. So now we have the species as H plus OH minus, the carbonate system HOH CO3 minus and CO3 2 minus, and also the H2S system, HS minus is 2 minus. So we have 1, 2, 3, 4, 5, 6, 7, 8 species. The charge balance is always there. So the charge balance would be the only positively charged species equal to all the negatively charged species. HCO3 minus plus 2 CO3 2 minus plus HS minus plus 2 S2 minus. So that's our charge balance. And in terms of the equilibrium, in addition to the K value, we mentioned that we have these two values that are related to basically the concentration in the liquid phase versus the partial pressure of the gas. So we can say HPM of CO2 would be equal to partial pressure of CO2 divided by the concentration of H2CO3. And HPM of S to H2S would be partial pressure of H2S, which is given, divided by H2S in the solution. So now we have, just keep in mind, as I mentioned, we cannot use alpha in our Excel spreadsheet. Rather, we relate every concentration to this value, because this is constant, and the concentration of other species to this value, which is basically constant. So now we need to revisit our equilibrium equations in order to find that relationship. So basically starting from the CO3 minus the first equilibrium constant for the carbonic acid. So basically Ka1 would be HCO3 minus times H plus times H2CO3. And we know H2CO3 is constant, so we can write HCO3 minus as a function of pH. So this would be Ka1 H2CO3 divided by H plus. So this would be, if you want to make it more involved, you basically can expand this H2CO3 to the partial pressure, but up to here it would be enough. So the second one would be Ka2, which is basically CO3 2 minus H plus divided by HCO3 minus that we just calculated. So then CO3 2 minus, by also inserting HCO3 minus, it would be Ka1, Ka2, these are for the carbonate system, times H2CO3 times H plus to the power of 2. So we can do the same thing for basically the H2S system. So HS minus, if we do that, HS minus similarly would be Ka1 of H2S times H2S that was previously calculated divided by H plus. And S2 minus would be Ka2, Ka1, H2S divided by H plus to the power of 2. So basically here we're not using that alpha notation because we cannot use it. Rather, we're just relating every concentration to something that we know, for example, the K, or H2S, something that was dictated to the system by the partial pressure of the gas that the solution was exposed to. And also we're looking at different pH to calculate these values. So the Excel sheet would be like that. So no alpha value, but rather looking at it like we're individually calculating individual species concentration based on what we know. So basically this is the Excel file. So we have always the swing of pH going from 0 to 14. And now this part, this was calculated based on the partial pressure and the Henry's constant, the same as this guy. But now these two species are calculated based on the equation that we just drove on the lecture. This is related to this one and the pH. So it was calculated and this was calculated as that. And for the H2S system, it was calculated based on the H2S and also the pH. And then we can do the charge balance as we do always, the left-hand side minus the right-hand side. And then we see that the change in pH is happening somewhere here. So between pH and 4 and 5. And then when we zoom in, we see that the pH is shifting here between the pH of 4.85 to 4.9. So here we brought the graph, as I mentioned, basically the pH is changing here between the pH of 4 and 5. And here is changing right here between 4.85 and 9, 4.9. So that's the pH is. the pH is roughly 4.85 for this system that was basically a pure water, but was exposed to two acidic gases, CO2 and H2S. So the pH was eventually 4.9. So the last part of the question is basically asking, now that we have this graph, so why not just looking at the PC-pH diagram? And more importantly, looking at the total concentration and how does that change as a function of pH? Because the difference between the open system and closed system is the fact that the total concentration in closed system is conserved, but here the total concentration is a function of pH. So that means if pH changes, the amount of carbonic acid and H2S that is absorbed in the system would also changes. So if we go back to the Excel file, we see that since we have all the concentration, so we can easily calculate the p-values for individual. And when we have the p-values for the individual, we can just construct the graph. And this graph would be basically from 0 to 14. And we're taking into account also the total concentration. So here, as you see, these are like the individual lines for individual species, but this one is the total concentration for the H2S system, and then this is the total concentration of carbonic acid. So basically what this tells us is that the total concentration of carbonic acid would significantly go down if the pH goes below 6 point or below 6. But on the other hand, the concentration of H2S would go significantly down for pH below 7. So that sort of information is pretty useful to evaluate at a certain pH what would be the contribution or how much of that particular system we have in the solution. So pretty straightforward. We talked about two different gases, and these two have like a combined combination, and we need to take into account both of them in the charge balance, and all the derived equation eventually are we have to put into the charge balance in order to evaluate the pH of the solution. So that's all about this lecture 15, problem solving of chapter 2. And we cover different aspects of acid-base, talking about how much we need to add to the solution to change the pH, or if we add something to the solution, what would be the initial pH? Or at the end, we talked about if we expose a solution to a certain atmosphere with certain composition of acidic gases, what would be the composition at equilibrium? And yeah, that's it. Thank you so much.